Hello, everyone. I am Adrenaline, the Bazooka Prophet, CEO, Adrenaline Global Online Educational Platform. Now, on the board is a follow up question to the previous question I did. So, if you have not watched that particular video, do well to watch it. Now, when I did the video, some students from uh, from international community sent me a DM and they said that I should use the arrow and X to determine whether a particular pair of compounds that are organic are enantiomers or diastereomers. So, in this particular video, I'm going to be taking my time to actually break it down for your understanding. So, I'll be doing just one of the question from my previous question. Then you can also try the rest on your own. If there's any question, feel free to DM me. If you want a one-on-one online tutoring, my DM is just a click from you. So let us go. Now, before we know whether a particular molecule is enantiomers or diastereomers, right, using the arrow and the X configuration, this tip must be in your head. For example, a compound is said to be uh enantiomers, right? For example, if I'm having two compound A and compound B, if compound A configuration for the arrow and X is arrow and arrow, in the case of B, right, it must be opposite, meaning arrow here will be X here, arrow here will be X here, meaning it must be no, uh, 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 it must be a mirror image and it must be non superimposable, meaning every of this configuration must be the opposite. Unlike that of the diastereomers, that if I am having, all right, if I'm having A and B as two compounds, right? In the case of diastereomers, there is always a some will match, some will not match. For example, if I'm having a compound A here, arrow, arrow, right? B here, one must be arrow, right? So that one can be X, meaning some will match, some will not match. That concept should be in you. In Okay, let us continue. Now, I'm having molecule A and molecule B. I want to determine whether it is using the arrow and X to know whether it is enantiomers or diastereomers. So what will I do? Now pay close attention to these two molecules. Now, the first step you must take note of is to be able to identify the stereo center or the stereo carbon or the chiral carbon. They all mean the same thing, meaning you will check each of the carbon, right, that is a chiral carbon, that is to say that is bonded to four different group. These are basic organic chemistry. Four different groups attached to a particular what carbon. Now, if I look at this particular structure here, right, you observe that there is a chiral carbon here. How do I know that it's a chiral carbon here? Of course, if you check this part here and this part here, they are not the same. This part here too is also different. Now, there is an invisible hydrogen that you do not show explicitly, but it's here. So here is 1, 2, 3, 4, right? So there's a chiral carbon here. Now, if you look at this particular one here, this particular carbon here, there is no chiral carbon here. Why? If you look at this part here and this part here, they are alike, they are similar, meaning you won't be able to determine any changes using the CIP, the Carl Ingold and Prelog, right? You won't see any differences here. So if meaning it is symmetrical, meaning if you even cut it from here, this side and this side are alike. So there is no chiral, there is no chiral center here, or there is no stereogenic center here, but there is here, because this side and this side are different. So in this particular molecule, right, there are two stereo centers here, which are one stereo center and two stereo center, or two chiral centers here. The same thing also goes here. So in this particular molecule here, we only have this chiral center here, this chiral center here, right? That is to say, this middle one here will make this side and this side to look alike. So for these two particular molecules, we only have two chiral centers that we can dictate our arrow and x from here. Now let us go. I hope you're following. Now let us go. Now follow me. Now based on the ingot and prelog determination, it is based on atomic or number, or where we have highly substitution. Now let's go here. So let us assign priorities to them here. Now this is the chiral carbon here. I'm to determine whether it is arrow and x. Now remember, arrow means rectus, meaning it is going clockwise. X means sinister, meaning it is going what now? Anti-clockwise. So let us go. Here is the carbon here. So if you check here now, here is, if you check from here to here is more highly substituted here. So this side here, we take 1, right? Here we take 1, right? Here we take 2. Here we take 3, and here we take 4. If you look at the way your eyes are going this way, meaning here is going in a clockwise direction, meaning I have my first what now? Arrow here. Now I move to this other one. Now be very, very careful here, this particular molecule, because of this dash that you have here, right? Now let's go. Let us assign priority now to this side. Now priority. Now if you of course, if you observe, here is highly substituted compared to here. So here we take 1, right? Here we take 2, right? Now remember, because this one here is dash, it means the hydrogen here will take this what? This wedge, which is like this here. So here is 1. This side is highly substituted. That's more carbon compared to this side. So here is 1, here is 2. Now here is 3, right? There's a carbon here. Here is 3, then here is 4. Meaning, if it is the way it is going like this. It is going in anti-clockwise direction. Remember, this side is anti-clockwise direction, which is what now? X. But there is a problem here, because we are told from the CIP that the least atom should not be placed in either the line or the wedge, right? Rather, it should be placed in the dash. And because hydrogen here is the least atom which is being placed here, you have to switch it. So instead of you saying X, here become what now? Arrow. So for this particular structure A here, I'm having my arrow and my arrow configuration. So let us now move to this particular one here, knowing fully well that we have one chiral carbon here and another chiral carbon here, or we have one stereogenic center here and another stereogenic center here. So let us work on it too. Now, of course, here is highly substituted, right? Here is highly substituted. So here we take 1, here we take what? 2. Here is 1, here is 2, here is 3. There is, of course, an invisible carbon here, an invisible bond here to make this carbon to be 4, because 1, 2, 3, 4. So here is hydrogen. So here we take 4. If you look at the way your eyes were operating, or where it was going like this, from 1 to 3. So it will go like this, which is what now? Arrow, right? So this particular stereo center here is arrow. Now let's move to this one here, right? Of course, here is highly substituted. So here we take 1, this side we take 2, here we take 3. Of course, there's hydrogen here, here we take 4. So the way it is going here, it is going in this anti-clockwise, which is X. So here I'm having arrow and what now? X. Now from what you are having here now, right, this is a typical diastereomer. How do I know it's diastereomer? I told you there must be partial mismatch. Some will match, some will not match. Look at it here now. Arrow and arrow match, but arrow and X do not what? Match. And this is how easy it is using the arrow and X to determine whether a particular compound is identical, enantiomers, or diastereomers. Now stay tuned, do well to like, share and subscribe, and do well to contact us for one-on-one online private classes. Thank you and God bless you. But meanwhile, before you cut the camera, look at the way it is. If you look at this particular carbon here, chiral carbon here, always look at the side. This side is more advanced compared to this side. Just visual explanation. Thank you and God bless you once again.